get started with today's lecture? No. Okay, well then let's get started. So what we began last time was chapter 1.3, or chapter 1, section 3, and we discussed the following two new kinds of propositions. We discussed tautologies. Can someone remind me what a tautology is?
It's a compound proposition where the propositions are always true.
Yep, truth value is always true. Can someone remind me of a way to construct a tautology using the proposition P, for instance?
P or not P?
Yeah, P or not P. This will always be true because the or returns true if at least one of the two propositions is true, and either P is true or P is false and not P is true. So, okay, this is tautology. We also discussed contradictions. Contradictions are very similar. What's the definition of a contradiction?
Proposition and the negation, so it's always false.
Yes, exactly. So it'll be a compound proposition which is always false, and we build them in a similar way. So compound proposition, always false. An example is P and not P. This will always be false. Okay, so these are important kinds of propositions that we need to kind of keep track of. And in particular, they're going to help us with the following important definition. So definition, compound propositions P and Q are logically equivalent if and only if Q is a tautology. In notation, we write this as P is equivalent, this is with 3 bars, to Q. So I just want to kind of give a brief description of what's going on here. The point is that we may have many different propositions So there are a huge number of propositions that we can come up with if we just use P's, Q's, ands, ors, negations. You can build longer and longer propositions with more and more terms, right? Like I can write down some terrible proposition by not P or not P and Q and P and not Q and P or P and Q, right? Like I can write down horrible, terrible propositions with very complicated expressions, but nonetheless, this is almost certainly going to be logically equivalent to something more simple. And so the idea is we want to consider propositions up to their truth values. Or in other words, we want to only consider propositions up to things that give the exact same truth values in every case. So you should be able to exchange two different propositions as long as they have the same truth values. And that's exactly what this definition is going for. Can someone remind me about the truth table for P if and only if Q? Or kind of what to think about when you see P if and only if Q?
They're true as long as they have the same truth value.
Exactly. P if and only if Q will return true if both of the propositions are both either true or are both false. And this proposition, P if and only if Q, will return false if they have different truth values. So if P if and only if Q is a tautology, that means for every possible combination, they have the same truth values. Yutong Wang, that's correct for these kind of propositions that we've been dealing with when they are only kind of two. But the truth tables can get more and more complicated if you start introducing more variables like P, Q, R, etc. But that's definitely the image of the truth table if you have like P, Q, etc. Okay, so does it make sense that compound propositions being logically equivalent means that, like this condition, P if and only if Q being a tautology, means that the proposition P and the proposition Q have the exact same truth values at every entry? Does that kind of make sense? I'll do an example. So for instance, let's show that not P or Q is logically equivalent to not P and not Q. Okay, well, we want to set up our truth table. So do I have enough space? Yeah, so P, Q. It's going to be kind of a long truth table because there are a lot of things that I need to show. True, true, false, false. True, false, true, false. So I need to do not P or Q. So just so that I don't make any mistakes, I'll do kind of the long version. P or Q is true, 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 false. And then if I take the negation of this, not P or Q, then I just take false, 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 true. And then if I'm trying to do not P and not Q, let me just kind of do all the little pieces. Not P is going to be false, false, true, true. Not Q is going to be false, true, false, true. And then not P and not Q is going to be false, 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 true. And now what we're trying to show is we want to examine this following proposition. Not P or Q, if and only if the proposition not P and not Q. So I've already written the two propositions that I'm trying to compare in these two columns, and the if and only if is going to go down each row and tell me whether they have the same truth values or whether they have different truth values. So what's the value of if and only if on the first column, or on the first row? Yep, it's true here. How about here? Yep, true here. The next one, it's also going to be true. And for the last one, it is also true. Let me make sure this pen's okay. So it seems like a kind of roundabout way of going through this, but what this definition is actually telling you to do is it's telling you write down the proposition associated to P, write down the proposition associated to Q, and then this if and only if being a tautology is checking whether they have the same truth values in every position. And in this case, since they have the same truth values in every position, this proposition, if and only if, is a tautology. So I call these two propositions logically equivalent. Any questions here?
I have a quick question.
Yeah, sure.
Why under the not P and not Q column, why wouldn't the first truth value be true since both of them are false? Or do they both have to be true?
So yeah, for and, they both have to be true.
Okay, all right, thank you.
Yep. So let's do a quick verbal example of this. Can someone give me two propositions? So proposition P.
Walmart is a store.
Walmart is a store. And I'll take the next one. Pancakes are waffles. These are phenomenal propositions, by the way, everyone. I'm really happy with these. So pancakes are waffles. I simply don't have the creativity to come up with the required amount of propositions. Okay, so let's make these two statements. So one is not P or Q. So can someone translate into words what this proposition is?
Walmart is not a store and pancakes are not waffles.
So just to make sure that I'm doing the right construction, I'm going to use the it is not the case that. So it is not the case that Walmart is a store or pancakes are waffles. Right? We agree that this is the kind of rote or routine way to negate a proposition. It is not the case that Walmart is a store or pancakes are waffles. And then let's also write down not P and not Q. Well, in this case, this is, it is not, well, here I'll use not. So Walmart is not a store and pancakes are not waffles. So here we can kind of see what this logical equivalence is telling us. This is saying if we want to negate an or statement, so it is not the case that Walmart is a store or pancakes are waffles, that's logically equivalent to the negation of both with an and. Walmart is not a store and pancakes are waffles. Any questions on this kind of analysis of logical equivalence? No questions here? Okay. Maybe it seems at the moment that this definition of logically equivalent propositions is kind of painful and tedious because I had to do extra work. Instead of just looking at these two propositions and checking that they have the same truth value, what I had to do was build this new proposition and check whether or not it's a tautology. But it turns out that this definition of logical equivalence is one that will extend well, so to speak, to more general logical propositions. So I just want to ask you the following question. How big is a truth table for a compound proposition that depends on n sub-propositions? Does anyone have an idea? Exactly. It's 2 to the n. 2 to the n, because essentially what we have to do is there are two options for each variable, for each sub-proposition that we have to check, either true or false. So there are going to be 2 to the n ways of choosing combinations of true or false for each sub-proposition. So you can see that the size of truth tables is going to get extremely large as we start adding more and more propositions. Thus far, we've only dealt with 2 propositions and maybe with 3 on your homework. I forget if I assigned you one with 3. So the point is, we want to use logical equivalence instead of truth tables. Because it becomes much more efficient in the long run. Okay, so what I want to demonstrate, I want to start kind of demonstrating this idea. So first, let's show that P implies Q is logically equivalent to not P or Q. So I would like for you to do this really quick. So I'll write down my own table, but I'll let y'all work on it for a little bit. P, Q, true, true, false, false, true, false, true, false. And now I'll start writing, hopefully after y'all. P implies Q as the proposition that has truth values true, false, true, true. And then not P or Q will have the truth values, well, false or true is true, false or false is false, false, true or true is true, and true or false is true. And then P implies Q if and only if not P or Q has truth values. Well, you just compare these. True, 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 true. So what do we conclude from this truth table?
They're logically equivalent.
Exactly. These are logically equivalent statements. So the proposition P implies Q is not the same proposition as not P or Q, but they return the same truth values. So if you're only considering propositions up to logical equivalence, these can be replaced. So I'll say this kind of once again because it bears repeating. Let's use these controversial propositions. P is equal to water is wet, and Q is going to be equal to a hot dog is a sandwich. So let me construct two different propositions. Water is, so here's P implies Q. And here is not P or Q. So P implies Q is water is wet implies a hot dog is a sandwich. And then and then not P or Q is the proposition water is not wet or a hot dog is a sandwich. The point is, and I'm glad that this has sparked such excellent discussion, the point is these are two different propositions but they have the exact same truth values. That is, whether if you decide P is true and Q is false, then these two propositions will have the same truth value. If P is true and Q is false, then these are both false. If P is true and Q is true, then these are both true. If P is false and Q is true, then these are both true, et cetera, et cetera, et cetera. Okay, so two different propositions, but they always return the same truth values. So they're logically equivalent. Any questions here? And I will not be answering any questions about the truth values of these propositions. No? Everyone's fine here? Okay, so what we want to do next is I want to show you something like this. So prove that the proposition not P implies Q is a tautology without using a truth table. I'll give you a couple minutes to think about this. Or, you know, write essays to each other about water. So can anyone tell me an idea or an approach that they want to try to use if they're not allowed to use a truth table to try to understand this? Oh, shoot. Actually, I probably can't do this example yet because there are, well.
The only thing I could think of was like verbal reasoning.
Verbal reasoning is helpful. Yeah. So
I'm not really sure how to go about that.
So I suppose really what I wanted to do here, which I kind of, this problem should actually come later, but the idea that I wanted y'all to use is the following. What I just showed you is that P implies Q is logically equivalent to not P or Q. So the idea to try to simplify this proposition, not P implies Q, is to gradually replace each of these implications with a logically equivalent proposition. So in this case, not P implies Q is logically equivalent to, well, first I'm going to negate the kind of outer implies. So this is logically equivalent to not P or P implies Q. Do we agree with this statement that I did here? That these are logically equivalent. How did I get there? So what I'm writing here is I'm making this not P to be proposition R, and then I'm making P implies Q to be proposition, I don't know, J. So this statement right here says P implies Q is logically equivalent to not P or Q. So what I can always do if I have an implication is I can negate the first term, not R, and then I switch the arrow to an or and then J. But then when I translate back, not R is the same as not P. I get the or, and then J is just P implies Q. Does that help, Catherine? Great. And now I can simplify. For instance, what's not P? That's just P, exactly. So this proposition right here is logically equivalent to P or P implies Q. Are y'all with me so far? I did this example too early. I should have done it later, but hopefully y'all can still follow what I'm trying to do here. Okay, what can I do now? I have a P or P implies Q. Is there any logical equivalence that I can try to do here? Same thing, yeah, exactly. I can do the exact same thing. This is going to be logically equivalent to, I leave the beginning bit just the same, P or, and then what goes here? Well, right, not P or Q. So in other words, this is the statement P or not P or Q, exactly. And then there are more simplifications on this thing that we haven't discussed yet that will essentially finish the job. But I suppose the idea that I would like for y'all to take away from this is that to analyze complicated propositions, instead of, so P or not P will always be true, right? Yes, that's correct. So maybe I should complete this using things that you don't know yet, and then I'll go over them. But this is logically equivalent to, I can swap the parentheses, so I can get P or not P or Q. This is by associativity. And then P or not P is true. So this is equivalent to a true statement or Q. And then if I have true or something, what truth value do I get back here? True. Right. So this is a sequence of substitutions that brought me from a complicated proposition, namely, oh yeah, I'm sorry, thank you, from not P implies Q, and I was able to show that this was a tautology, without using any truth tables, but just by using substitutions of logically equivalent statements that in some cases you knew, and in some cases maybe I haven't spelled out formally. Any question here? So in the long run, this will be much better much more efficient than truth tables. Okay, any questions here? Do we need to show why P implies Q is equivalent to the negation of P or Q for homework? Starting now, I would say no, because we checked it very explicitly on, where did we check it explicitly? We checked it explicitly here. So now that we've checked it explicitly here, you can just use this on your homework freely. Okay, so the next thing that I'm going to do is I'm going to give y'all a big list of equivalences that you should start using essentially with their names. And on the homework, honestly, it's a good exercise to ask y'all to just prove all of these yourself because it's not that long. So I'll see about that. Okay, so big table of equivalences. Okay, so the first ones are going to be the identity equivalences. So these are P and T is equivalent to P, and P or false is equivalent to P. Okay, so in this case, it's very easy. So these are the identity equivalences. And of course, we can check this very easily by truth table. I'm going to have P being true or false. I'm going to have a proposition true, which is true and true. And then P and true is going to be true here and false here. So we see that P and true have the exact, oh my gosh, have the exact same truth table. So to be very pedantic about this, P, if and only if P and true has truth table true, true, since P, if and only if P and true is a tautology, I hope it's not. Since this is a tautology, I can see that P and true is logically equivalent to P. And then P or false is done just as easily. Everyone happy with what I did here? The next are the, obviously. All three of them. Okay. Next are the domination identities. And these are given as following. P or true is congruent to true, and the P and false is, I shouldn't say congruent, it's logically equivalent to false. And this is also just as easy to see. Let's do the second one in this case. So P, I get true, false, and then P, and then false is just false everywhere. And then P and false is false here and false here. And oh, what do you know? That's a domination. There's an I here. Domination. I didn't make up the names. Okay. False and false. So these are logically equivalent. F, if and only if P and F is true and true. Since P, if and only if P and F, F, if and only if P and F is a tautology, we see that P and F is equivalent to false. Is this okay? These ones are very easy because the truth tables are so tiny. Notice that these domination identities are what I should have used, or so this domination identity says any proposition or true is just true. I replace any proposition or true with the proposition true. That's exactly what I used here. So to go from T or Q to T, here I use the domination equivalence. Okay, I've got 10 more minutes to keep going. Okay, next we've got the idempotent identities. So these are P or P is equivalent to P, and P and P is equivalent to P. These are pretty easy to show. I mean, all these can be shown pretty easily using truth tables. So these are idempotent equivalences. Next, we have double negation, which is the proposition that not P is logically equivalent to P. We use this technically over here. To go from here to here, we used double negation. And then here we have the commutative laws, or commutative equivalences. So P and Q is equivalent to Q and P, and similarly P or Q is equivalent to Q or P. Once again, this is done via truth tables, but these are very easy to see, so I won't show these. Now we get to some of the more interesting ones. Well, that's up for debate, but P or Q or R is equivalent to P or Q or R, and similarly with and. P and Q and R is logically equivalent to P and Q and R. So now we're starting to get into, like, if we wanted to confirm that these are logically equivalent, we would need a rather large truth table because we have 3 variables floating around. So it would need to be 8 rows. So these are associativity. Now come some extremely important ones that I would like for you to pay a little attention to. Except I've hamstrung myself and given myself less space. So P or Q and R is logically equivalent to P or Q and P or R. And similarly, P and Q or R is logically equivalent to P and Q or P and R. So these I'm going to show, or at least one of them. So I want to point out something. You can view this kind of like expanding out a polynomial. Yes, exactly. It's exactly like distribution when you're dealing with polynomials. So this is called distributivity. And a very important thing to notice is how the symbols change. So if you have P or Q and R, you apply the P or piece to each. What's under double negation and domination? Double negation. So this is idempotent. And this is commutative. Okay. So notice that when you distribute P or Q and R, it goes P or Q and P or R. And similarly, if you distribute P and Q or R, it's the P and that gets applied to both. I have a P and Q, and I have a P and R, and they're joined in the middle by the or. Notice too that in both of these cases, the distributivity identity or the distributivity equivalences, they only apply when you have opposite symbols, when you have an and an or, sorry, an and an or an or and an and. You can't apply distributivity if you have two ands or two ors. So let me just finish writing the rest of them, and then I'll try to show one of these using truth tables. Here are some other important ones. Here are De Morgan's laws. Not P and Q is equivalent to not P or not Q. And similarly, not P or Q is equivalent to not P and not Q. We proved one of these earlier today. I forget which. But in any case, what this shows you, oh my gosh. What this shows you is how to negate and propositions or propositions. And notice that when you negate, you apply the negation to each symbol, and then you flip. The and becomes an or, and if you started with an or, it becomes an and. Here are De Morgan's. Absorption. The absorption laws are P or P and Q is equivalent to P, and P and P or Q is equivalent to P. And then lastly, we have the propositions called negation. P or not P is equivalent to true, and P and not P is equivalent to false. Okay, big list. My hand hurts from writing it now. Don't need to go to the gym for weeks. These are all equivalences that you will need to become comfortable using, and also, at least for the most important ones, you want to know their names. You'll get used to these by doing homework with them and using them to replace more complicated propositions with equivalent propositions. What I want to do is I want to prove the distributivity, one of these, using a truth table. Any questions before I move on from this gigantic list, by the way? No? Okay. What about P implies Q is equivalent to not P or Q? That one doesn't have a name, but that one is extremely important to remember. Yeah. That's actually one of the first things that you should remember whenever you see a P implies Q. But it doesn't have a name, and I'm not listing it in this big table. Okay, so let's prove, using a truth table, P or Q and R is equivalent to P or Q and P or R. Well, this is just going to be terrible, but I'm just going to do it. Hopefully this is the last big table that I do, and only y'all have to do the rest of them, and hopefully only for a little while. Okay, so true, 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 false, 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 true, true, false, false, true, true, false, false, and then R is going to be true, false, true, false, true, false, true, false. I would ask that if you do truth tables with 3 propositions, you use exactly this in terms of first 4 are true, second 4 are false, then here it goes by 2s and here it goes by 1s. This makes it much easier to check your work. Okay, so now let me do Q and R. This is going to have, just checking here, true, false, 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 true, false, false, false. So when I do P or Q and R, I'm taking the or of these 2 columns. So that's going to be true, 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 false, false, false. And now I do, oh, what a pain. P or Q, I'm just slow. Maybe y'all can see this faster than I can. P or Q is going to be true, 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 false, false. And then P or R is going to be true, 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 false, true, false. And then if I do this and this one, then I get true, 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 false, false, false. And now I can check. Is it the case that P or Q and R is equivalent to P or Q and P or R? And I just check these lines of the truth table. And since they return the same truth value in every case, I conclude that these propositions are logically equivalent. Any question here? So the big idea that I want to kind of get across to you is, first, truth tables are quickly going to be impossible to apply to the situations that we want to, right? Truth tables were great for playing around with 1 or 2 propositions, but as I start adding more and more propositions, it's going to be totally impossible for me to start writing down truth tables for these things. So that's the first thing to note. The second thing to note is that I can use truth tables to prove this collection of identities. And then what becomes much more efficient when I'm trying to analyze the truth values of propositions is I use these equivalences instead of writing down truth tables. Okay? Any questions here? Well, that's about a day. So I'll write up your homework problems for the new homework set in probably like a half hour or something. Have a nice day, everyone, and stay safe as much as it is possible.
Thank
So
you.
long.
Thank you.
I just
All right.
wanted to, if you're still
Yeah, go on. I'm going to stop